made on the percent area. So, I promise I'll never leave again. It's all my fault. However, the final exam is what's called cumulative, which means it covers the entire course. So you will see it again on the final. Not a whole lot, but there'll be some problems on the percents.
Do you have a
Question?
when is the final?
When is the final? I'd have to look at a calendar for that. It's usually the first week in June, or maybe the last week in May. I think it's the first week in June.
Someone asked, can we have a cheat sheet for that?
Yeah.
Okay, how many?
Getting to write smaller and smaller.
Just bring a magnifying glass.
Emotional dependency on your future. You abandoned us for a week.
I know. It's so shocking. Well, I apologize. Okay, we're going to chapter 8 now. And chapter 8 is basically it's about geometry. The word geometry is a Greek word because they did most of the work on it. These 3 letters mean earth,
I thought that was a cost.
and these 5 letters mean measure.
Estimate.
So this whole thing comes from figuring out how many acres of land you have and how many acres your neighbor has and all this kind of stuff. It's earth measurement. And it's very physical. It's got a nice, visual kind of component to it. There's a lot of new words here, new jargon with geometry that we have to learn. And also, it is a bit right-brained in the sense that you have to be able to see relationships as well as use formulas and equations to find things and so forth. Geometry is a very strange thing. I mean, every mathematician admits to it. We have to have it, we need it, but at the same time, there's a lot of evidence that we don't know what we're talking about at all. For example, the very first definition in geometry is that of a point. And you say, well, what's a point? Yeah, that's the problem. You want to know what your book says? A point is a specific location in space. When we often symbolize a point by a dot and label it with a capital letter such as P. Okay, and most people don't see anything wrong with that, That's a point, labeled P, okay. The problem is if you look more deeply into it and you ask for a better definition, you find out that a point has to have no width, no height, no nothing. It can have it can occupy no space at all.
So it's in your mouth.
I don't understand that.
See the problem now? Because the next logical statement is, then it doesn't exist. That's right. That's correct. So all of geometry is based on the idea of a point, which doesn't exist. Okay, that doesn't bother most of you, I can tell. Boring you, so I'll go on with this. But it bothers mathematicians an awful lot. Okay, so has no dimensions. In other words, no width, no height, no nothing. And yet we assume we know what it means. Now everything else is going to be based on that definition. So everything in geometry is quite questionable. For example, we're going to talk about a line now. This is the point. This is the line. Now your book defines it as infinitely many points that follow a straight path.
It's contradicting itself.
Yes, it is. So this is the way the basic level of geometry is taught. It's foolishness, mathematically. Okay, they're putting down words they hope you will understand. I mean, your authors are very good about that. But You know, truly speaking, these are not mathematical definitions. Infinitely many points that follow a straight path. Okay, we'll call that a line. Usually what they do is they take 2 points on the line, we'll call it A and B, and they use those to label the line itself. And because it's infinitely many, and because we can't draw infinity, we use arrowheads, meaning this keeps on going and this keeps on going. So that's the actual official picture of a line. And we write it this way, we write it as AB, and then we put this little double arrowhead thing on above it, and that's how you label the line. Now, could you label this line BA? Yes, you could. Those would be exactly the same thing. In other words, what's the starting point and what's the ending point make no difference, because it's infinity, so you can go in either direction. Now, a segment of a line, well, that makes a little bit more sense. Is a portion of a line between 2 points, including the endpoints. So the picture would look something like this. Here's A and here's B, and that's the segment of a line. Why is that important? Because you're going to be looking at geometrical shapes, and they're all made of line segments. Triangles, rectangles, stuff like that are all built up of line segments. So they're important. Labeling for this, again, AB, but because you don't have arrowheads here, you've got a finite chunk of line, you just put a bar over it, like that. Or BA, that's fine too. Okay, the next one which we'll need is called a ray. Is a portion of a line starting at one point. And that point is called the vertex. So instead of having a line go infinitely in both directions, what you've got with a ray is you start here, let's say at point A, and you go out in some direction. Now, that does go out to infinity, but it stops back here at A. So you don't put an arrowhead on this part because that's the beginning of the ray, so to speak, and it's also known as the vertex. And you can label the ray the same way. You can put another point out here, call it ray AB, but instead of having a double-headed arrow now, you only have a single-headed arrow. And you start the ray, you put the point A at the beginning of this symbol. In other words, if it was starting at point B, then the B would be here. The very first part of that symbol is the vertex. It's called AB. BA would not be right. BA would be a different ray. If you're talking about BA, then you'd have to start at B and go back in the other direction. So it would look like this. This would be BA. Not the same. Okay, then something interesting happens. Something called an angle.
Oh, excuse me. Sorry. I'm curious about, like, BA going that way. Oh, so BA isn't the same as AB for this one? For the
For
segment?
this one, it's the same. Yes, you can write this as BA. That would be the same line segment. But for this one, it would be different. BA would be the ray going back this way, and AB would be the ray going up this way.
Okay, I
Different
got it.
directions.
Thank you.
Yeah. Okay, now an angle. This is important. We're going to spend a lot of time with these. An angle is a figure formed by two rays, starting at the same point.
Bless you.
Thank you.
So you start out with the vertex, and let's say you have a ray that goes somewhere up here. We'll call this A. We'll call this point B up here. So this would be ray AB with the one-sided arrow up above it like that. Now the second ray would come down, but start at the same point, A, and it goes down like this. So let's call the point down here C. This would be ray AC. And that space in between the two rays is called an angle. Sometimes your books will put a little curved arc in there like this. And you can call that angle, you can label it, so to speak, in a couple different ways. One of the most common ways is to use that little angle bracket like that to indicate I'm going to talk about an angle now. And then you take the three letters to label the angle, but make sure that the vertex letter is in the middle of it. So you could do something like this, angle BAC. Or you could call that angle CAB. All you want is the A in the center. The A indicates the vertex. There's another way to label these. Very often books will put this little curved arc in there, and then they'll call this something like X. It'll be a lowercase x. And then they will say, oh, we can also call that angle X. And that's fine. So you see both of those. I think your book actually does both of those. Now, angles turn out to be very important in geometry, but only if we can measure them. We have to actually be able to measure the space between two rays. And the way that's done goes way back to thousands of years ago. We've talked about a circle several times. What happens with a circle is the Babylonians, who really were very interested in circles, developed a measuring process. And they actually got it from the number of days a year, 365 days a year. Well, that was good enough for them. They started looking at multiples of 60. For example, the phase of the moon is 30, which is half of 60. You can start talking about the number of days in a year, 6 times 60 approximately. So they did a lot with 60s. And they found out that once a year, the sun would appear in exactly the same point in the sky that it had been a year ago. And therefore, they reasoned that the sun was going, shall we say, around a circle. Now, this is way before we had our sun-centered solar system, way before people like Galileo and stuff like that. This was thousands of years before. But they all talked about, oh, the sun's going around the earth. Not obvious, but that's what they thought. So they put a certain number of degrees in that circle, which related to the number of days a year. And unfortunately, the abbreviation for degrees is exactly the same abbreviation as it is for temperature degrees. That's one of the big oops in mathematics. But it goes like this. If you start here and start going around the circle this way, let's say, counterclockwise, and come all the way back to here, you travel 360 degrees. That's a whole circle. Now, to try and draw 1 degree on there would be very hard. I couldn't do it with this kind of stuff, because this is wider than 1 degree. Okay, it's a very small measurement. there's 360 of those as you go all the way around. Okay, but we can chop it up a bit. Let's go up a quarter of a circle. Well, you'd think that that would be 1/4 of 360, and that's right. This angle right here, which is often designated with a square rather than an arc, is a 90-degree angle, which is 1/4 of 360. A straight angle, which goes all the way around to the other side here, because it's called a straight angle because it forms a straight line.
Thank you.
That's going to be 180 degrees. So that would be this measure right here. And of course, all the way around would be twice that, which would be 360. Once in a while, you need to know that this one down here is 3/4 of a circle. So it goes like this. That's 270 degrees, 3/4 of the circle. So that's our basis for degree measurement. In other words, we might say, well, what's the size of this angle right here? Well, that angle, you can tell it's less than a 90-degree angle, because a 90-degree angle would have to go up like that. So it's less than 90 degrees. So it's somewhere over here in this area. Who knows? Maybe it's something like this. I'm just eyeing it in here. Angles that are less than 90 degrees, like this, are called acute angles. But greater than or equal to 0. And if you go beyond 90, if you go, let's say, let's take it all the way around to here. Suppose we talk about an angle that is formed like that. That angle is greater than 90, but less than 180. That's called an obtuse angle. So so we know that's acute. We don't know exactly how much it is. Everyone okay? Sometimes we have allergies. This is something called a protractor. Now this is, meant to be used on paper. I'll try and use it to get that angle here, but they do make board protractors, but darned if I can find one since they redid the building. So I'll have to use this one. And what happens is very simple. They simply take a mark here that's so small that it's kind of hard for you to see, I'm sure. But as you go from one side to the other, let's say this side over to this side, there's 180 of those little marks on there, which means each mark represents a degree. Up to here you get 90 and so forth. There's a center down here, so you can put that in the center of your vertex. You put the vertex right there, and then line up the two rays and figure out how many degrees you have. It's a very simple idea. So, for example, I'll put this right here. Here's my vertex. I line up this side with this bottom ray AC, and this one goes to about 71. So this is approximately a 71-degree angle. And that would be an acute angle it's between 0 and 90. You can get these, the Staples and places like that for about $1 if you want to help out in your homework and make it a little bit easier. They've got a nice picture of one. I'm not saying to cut up your textbook, but they do have one that is made to scale in the textbook. It's on page 466. Now there's some relationships that you should know about because they do happen in geometry. Again, more definitions. Two angles that are equal in measure. They have the same number of degrees, in other words. Are called congruent. So now you can speak geometry at dinner tonight, and everyone will think you're just brilliant. Two angles that add to 90 degrees are called complementary. And two angles that add to 180 degrees are called supplementary. So, for example, let's say I have this one in black here that I drew in black to begin with. This one right here. That angle right there, and the leftover as you go down to the straight angle. These two angles are called supplementary because they add up to 180. And another way of saying it is, the larger angle is the supplement of the smaller, and the smaller is the supplement of the larger. That's also another way of putting it. You can do a little bit of math here with this. Let's say you have a 175-degree angle. Okay, that's not 180, so it's not quite all the way to a straight angle. It would be just a tad less than this over here. Okay, they ask you, what's the supplement of a 175-degree angle? Well, the way you figure it out is simply subtract it from the 180. And you get 5 degrees. So a 5-degree angle would be the supplement of a 175-degree angle. Okay. Let's look at some lines. Wish I had 2 rulers, but I don't. Well, I can just pretend my arms. If you have 2 straight lines, there's actually 2 things that can happen. 3 things technically. One is that they're actually not different lines, they lie on top of each other, which means they're the same line. That's the most boring case of all, and who cares? Or you could have 2 straight lines intersecting like this. And they have an intersection point. We'll look at that in just a minute. You could also have 2 straight lines what's called parallel to each other, which means they're railroad tracks. They never meet. They keep on going to infinity. And the angle between them is 0, but they're not the same line. They're different lines. Your picture is on page 467 at the bottom. So what we're going to do is take a look at all 3 of these situations as time goes on. Right now, the interesting one to us will be intersecting lines. And the picture would go something like this. When you have 2 lines intersecting, you've got 4 angles formed. We'll call it A, B, C, and D. The angles A and C are called vertical angles. Likewise, angle B and D are also vertical. In other words, they're opposite each other. And if you look at this thing for a while, you'll probably come up with the right result, and that is vertical angles are always equal to each other. They don't bother to prove this. That takes trigonometry that's way beyond our course. So it's just they're depending on you looking at it and saying, yeah, this angle, which would be, this is an obtuse angle here. It's bigger than 90, a little bit bigger than 90. And this angle up here looked like they'd be about the same size. And this one over here, which is less than 90, this is an acute angle, looks like it's about the same size as this one over here. So, in other words, vertical angles are always equal. So that's a geometry theorem that, of course, is beyond us to prove. We're just going to accept it as being true. The second thing that can happen is parallel. And just to get a picture of it up here, something like this goes on. Now, of course, I have not, precisely made these parallel. They look like they're not quite parallel. Very often lines are labeled with a letter, a single letter, instead of a double letter. This would be called line 1 and line 2, something like that. But the idea is they never intersect, so there's no angles formed with these at all, until you do something like this. You bring in a third line. Now the third line is not parallel to either of these. It's given a name, a fancy name. It's called a transversal. And that does form a lot of angles. In fact, there are two sets formed, and maybe you've already seen it as you're looking at the diagram. These sets look like they're very similar. So let's start labeling down here. Here's the first intersection down here. We'll call that angle 1. This will be angle 2, 3, 4. Up here, second intersection, 5, 6, 7, and 8. Now, there's a lot of symmetry here. Hard to tell this from this. If you look at them, take a good distance and say, they look very symmetric. And that's true, they are. And of course, math is not content to say, oh, they're symmetric. Math has to be very precise about it. So here's the precise definitions of all these things. There's lots of angles here, and they fall into 3 categories. The first category is called alternate interior angles. Now, luckily, the names here tell you what's going on. Alternate refers to the transversal. Now, the transversal is this one that crosses the 2 parallel lines. And when you say alternate, you're talking about alternate sides of the transversal. So these angles are going to be on opposite sides of the transversal. Interior refers to the parallel lines. This is the transversal idea. This is the parallel line idea. Okay. Opposite sides of the transversal, but inside the parallel lines. Parallel lines are these two. They have an inside, but then they have an outside too. So we want to be inside, but on opposite sides of the transversal. Let's see what that might be. All right, let's start out with, let's say, number 2 here. Now, we want another angle, which is on the other side of the transversal, but still inside. How about that, number 8? And it turns out, as you might guess, just by looking at this roughly drawn diagram, that 2 and 8 are equal to each other. Yeah. Angle 2 equals angle 8. And you say, well, how about the other one? Suppose we did this one. This is also alternate interior. This is an obtuse, and this is an obtuse. Are those 2 equal to each other? Yeah. Angle 3 equals angle 5. That's true. Okay, the next category is going to be alternate exterior angles. again, on alternating sides of the transversal, but now exterior. So let's start out with something like number 1 down here. Okay. We want to be on the other side of the transversal, but outside. Just the parallel lines. That would be a number 7, wouldn't it? So angle 1 equals angle 7. And there's another pair, huh? What have you here? Okay, you've got angle 6. The one on the other side of the transversal, but outside, would be 4. The third category is called corresponding angles. Now, corresponding angles, we actually have to write down the definition because corresponding doesn't mean too much. All right, these are on the same side of the transversal. But one interior and one exterior. Okay, let's see if we can find something like that going on. Let's get a different color here. Oh no, out of colors. All right. Same side of the transversal. Okay, that means we're either below the transversal or we're above the transversal. But we want one on the inside and one on the outside. Okay, let's choose number 5 here. That's inside between the 2 parallel lines, and it's below the transversal. And if you go back over here on the same side of the transversal, but outside the 2 parallel lines, you get this. So number 5 and number 1 are equal. Step on it. Any other corresponding? Sure. How about this one here? Angle 6 and angle 2. Now let's go above the transversal. Okay, you've got angle 8 here. Go outside, that would be angle 4. And of course, you've got the other one left, that's angle 3 and angle 7. Now, after all that, you might say, well, is everything equal to everything? I mean, are there any different angles there? Yeah, there are 2 different angles, but otherwise, they're all equal. Now, here's the strange part of it. Let's say we go back and erase one of these numbers and put in an actual number of degrees. Okay, I'll just erase this one here. It's no longer going to be called angle 6. I'm going to measure it, give it some number of degrees, and write it up there. And it looks like about 37 degrees. Okay, so we know one angle, right? Now watch what happens. What do you think?
Yeah.
It's all going to fall apart.
I don't think so.
All you have to do is know one angle. That's all there is to it. Okay. If this is 37, what's 8?
37.
It was the vertical, that's right. Okay. If this is 37, what's 2? 37. That would be corresponding. This is 37. If this is 37, what's 4? 37, because they're vertical, right? So this is getting kind of boring. All right, up here, you've got a straight line. This is 37. 7 is the supplement of 37, right? So to figure out how big it is, we take 180 degrees and subtract 37. And that gives you 143 degrees. Now, if this is 143, 5 is 143, right? And likewise with corresponding angles, this would be 143. And this has to be 142. So all 8 of them are known if you know one. One angle determines the whole thing. Now, the reason that happens is the reason we had right back in the very beginning. It's all the symmetry. It's very symmetric. So what goes on in one intersection goes on in the other intersection. You can see they're identical. They're copies of each other. Huh? So this is math's long and torturous way of saying, yeah, they're symmetric. I mean, I really do appreciate mathematicians. I have a lot of friends that are mathematicians. We used to say when I was going to college, every physicist should have a mathematician as a pet.
As a pet?
They didn't like that at all. But I had several pets. And I called on them when I needed them. They're really amazing people. You know, they have very clear, sharp minds. But if you ask them, well, does this have any practical use? They'll look at you like you're crazy. Have practical use? Yeah. Oh, okay. So there you go. But what's really weird about this is if you look at the history of mathematics, especially the 20th century, they came up with discoveries in their ivory towers, never ever looking at the world. They came up with something called group theory in 1930s, 1940s, and everyone said, oh, nice. And they went on about their business, you know. Group theory, they thought, it's a funny thing in mathematics. You know, they're just fooling around with their minds. 20 years later, 25 years later, they were investigating elementary particle physics, and they were getting all these particles that they'd never seen before coming out of their theory called the standard theory. The only thing that organized those particles was group theory, which was done 25 years before. And this happens again and again. Mathematicians keep finding things which, you know, a quarter of a century later are useful. Why do they do that? Nobody knows. All right, here we are, 8.1. Let's do some homework. Anyone who hasn't got their test, come on up.
Saturday.